Good afternoon. Today we're working on exercise 13H, exponential models and applications. This is the last exercise in this chapter, and what we're doing is combining all of our knowledge of exponential graphs and equations in order to help us answer practical problems. Exponential modeling is common in science, especially growth and decay. Growth such as cell division and decay such as radioactive decay. Now the particular exponential equation that's used to model these things are as follows. So please copy this down on your handout if you have one. A equals A naught times lowercase a to the power of b times t. The particular parts of this equation stands for A is the amount you get after a certain amount of time passing. So t would be time. A naught, that represents initial amount. Consider what's going on when you are at your initial amount. Initial implies that the value of t is equal to 0. So any base to the power of 0 is 1. When t is 0, this part becomes 1, and 1 times the coefficient in front gives you your initial amount. Then here we have the base. At the bottom it says growth is where a is greater than 1. So that makes sense, because if your base is greater than 1, when you repeatedly multiply the base, then your amount gets bigger and bigger. Decay is where a is between 0 and 1, which makes sense, as if you multiply by a number that's between 0 and 1, your amount gets smaller and smaller each time. Now let's apply this equation to the following question. The number of bacteria in a culture, capital N, is given by the exponential equation. Capital N is equal to 1,500 times 2 to the power of 0.18t, where t is the number of days. Just reading through the other questions, I can see that I'm going to be subbing in or solving for the polynomials in this equation. So a great thing to do is, if you have your CAS, start by defining this equation in your CAS in function notation. Okay, and here's what we do. We say that we're going to use function notation now. So we say let n of t equal 1,500 times 2 to the 0.18 t. And I'll do that in my CAS. Opening up a new calculator part, I use the letters n and t from the keypad below. N of t is defined as Control, then the button next to 9, 1,500 times 2 to the power of 0.18 times t. Okay, enter. And that's done for us. Now to answer the first question, find the initial number of bacteria in the culture. We say let t equal 0. That's a very important step. So when we place that in our calculator, we should get n of 0. 0 is our input for time, and our calculator says that it's equal to 1,500. Okay, notice the initial number of bacteria was 1,500. That's because they've replaced t with 0. So 2 to the power of 0 is 1, and 1,500 times 1 is equal to your 1,500. In addition, that 1,500, which is the coefficient of this power, that in itself gives us our initial amount. Remember, the coefficient of the power gives us the initial amount. Now let's use our calculator to figure out the other questions. find the number of bacteria to the nearest 100 after 5 days. So after 5 days, we let t equal 5. In our calculator, that would mean n of 5 is the same as 2799, and so on. And we can round that to the nearest 100, which will give us 2,800 bacteria. After 10 days, we let t equal 10. So n of 10 is equal to, and you can see there, 5,200 to the nearest 100. Next question, how many days does it take for the number of bacteria to reach 9,000? This time around, we're trying to find time, and they give us the number. So in other words, the equation we set up is n of t equals 9,000, and our calculator can solve this equation. So, solve gets a menu in 3 algebra, then 1 solve, and we type this equation in. N of t is equal to 9,000, and we're solving it for t. And that tells us that the time that occurs is 14.36 days. Lastly, we need to sketch a graph of n versus t. Now with this model, we expect to see growth. So we need to find a few points to plot our graph and then make the graph curve upwards. First I start by sketching my axes. Notice I'm only sketching the quadrant 1 because I know all of my values will be in the positive region. Now I've got an initial value of the number, which is 1,500, so I can label that in. Excuse me. And I also know, after 14.36 days, I get 9,000 bacteria. So 9,000 is going to be up here, and 14.36, and we place our coordinate. Then we make sure our graph is curving upwards to show that we have exponential growth. Now lastly, make sure your graph does not cross the vertical axes because time starts at 0. But your graph can keep going. Place an arrow there because the question has not stated that the experiment ends at some point, so we assume that it keeps going. Okay, let's work on question 2. The points 16 and 596 are known to lie on the curve y equals a times b to the x, where a is greater than 0 and b is greater than 0. Find the values of a and b. Let's work through this by hand first, and then also show how we can do this on the CAS. By hand, that implies that if we're trying to find the values of a and b, we need to know what the values of x and y are. But they've given them to us in terms of coordinates. So let's sub in the x and the y values into these equations. So x, y, that implies y is 6 and x is 1. In the equation, I get 6 equals a times b to the 1. Subbing in my next coordinate, I get 96 equals a times b to the power of 5. So we get two equations, and we can use that to solve for our two unknowns. Let's label these equations 1 and 2. For this type of equation, we'll try to cancel out one of the variables, and the variable I'm looking at is variable a. To cancel out, I can divide these two equations by each other. So if we take equation 2 divided by equation 1, what we get, just working through each of these terms, 96 divided by 6 gives you 16. The a's cancel out by division, and the b's become, well, b to the 5 divided by b to the 1 is b to the 4. So now we can solve this equation for the value of b. b to the power of 4 is equal to 16. So b would be equal to plus or minus 4th root of 16. Be very careful here. We get two solutions because b had an even power. If we raise the 4th root of 16 by 4, we get 16. If we raise negative the 4th root of 16 by 4, we also get positive 16. At the end, though, we have to reject one of these solutions because we know that both a and b are greater than 0. So we write, therefore, b is equal to the positive 4th root of 16, which is equal to 2, and our reason was b is greater than 0. Okay, at this point we've found b, now we need to find a. Finding a is pretty easy because in our two equations, if we know what b is, a can be solved. So let's sub into equation 1. That gives us 6 is equal to a times 2, so a is equal to 3, and we have our two solutions. Well, not solutions, we've got our two values for a and b. So these are our two solutions. Now let's do this by hand. There's a few ways to, let's do this by CAS. To do this by CAS, there's a couple of ways. One way is to define it as a function, and then using the simultaneous equations solver to solve that function. Let f of x equal a times b to the power of x. So this is our function notation. Let's define it in our calculator. F of x is defined as a times b to the power of x. Notice I place the multiplication sign in between a and b. That lets the calculator know that we're implying multiplication instead of ab being a single pronumeral. So we press enter, that's done, and now we solve this simultaneously. Through menu, then 3, then 7, then 1, solve systems of equations. We've got two equations we're going to use because we've got two coordinates. But the variables we're trying to solve for are a and b. So let's change this to a and b. And press enter. Now the two coordinates, how they help us, is that if we know what the x value is and we know what the function equals to, we can write that as our two functions in our calculator. So our two equations, so to say, would be the result of f of 1 equals 6, when x is 1, y is equal to 6. So that's equation 1. And equation 2 is f of 5 equals to 96. That's equation 2. f of 5 equals to 96 comes from our coordinate. So these are the two equations that we can enter into the following boxes. F of 1 is equal to 6, and f of 5 is 96, and we solve for a and b. And we notice that we've got two pairs of solutions, one where a is negative 3 and b is negative 2, and the other is where a is 3 and b is 2. Obviously, we must only accept the positive solutions, but we still need to write down all of the solutions as part of our working out. So we would say, therefore, A is -3 and B is -2, or A is 3 and B is 2. Then at the end we reject one and accept the other. Therefore A is 3 and B is 2, because A must be greater than 0 and B must be greater than 0. And then we also get the same solutions as what we got before by hand. Now we're moving on to the next question. So this is a question where we are modelling population growth. So in question 3, the populations in millions of P and Q of two neighbouring American states, capital P and capital Q, over a period of 50 years from 1950, are modelled by the functions, and the functions are given, where T is the number of years since 1950. Plot the graph of both functions. Now let's do this by adding a new page in our calculator document. Excuse me. Add a new page by pressing Ctrl Doc, and we add the graph. Now the graph we're going to add are based on these rules, but be careful, our graph can only recognize x and not t, so we're going to take the t and turn it into x. Our first one is 1.2 times 2 to the power of 0.08 times x. Okay, and we get our first graph. Our second graph is the result of 1.7 times 2 to the power of 0.04x. So we get our two graphs. They look like they are approaching an intersection, but we're not sure, so let's change our zoom settings. The question has given us some information about the domain of this graph. In particular, the time occurs over a period of 50 years. So we expect the maximum x value to be 50. I changed my zoom setting through menu, then 4 for window zoom, then 1 for zoom window settings. So x minimum I might change it to -5, and x minimum I might change to 60, so that our value of 50 will be shown in the window. Our y minimum, let's change it to, we can do a bit of trial and error, let's call this 60 as well. Okay, and then we get our graph. Keep in mind that you don't have to use the window settings to change your zoom. You can also double tap the number up there next to the axes. That shows us what the maximum axes value is that the calculator is showing. So let's change this to something smaller, 20. Okay, and I think that looks like a good graph. Now plot both functions. That implies, well, before we sketch our graph, let's take some coordinates on these graphs. So we take these coordinates by using our trace function, menu 5, then 1. Right now the spider's on our blue graph. Keep in mind that to go between your graphs, you can press the up or down button. That allows the spider to cycle between your two graphs. I'm going to make it go to the vertical intercept by letting x be equal to 0. Okay, and for our red graph, we have the coordinate 0, 1.7. For our blue graph, it's 0, 1.2, which makes sense because they are our initial values in the equations anyway. Now let's start making our graph. Horizontal axes for time, then vertical axes for the following populations P and Q. P, Q. So our two x-intercepts were 1.2 and 1.7. I'm going to make them quite close to the horizontal intercept because it looks like it is on our CAS. So 1.2 and 1.7. And then for the maximum value, which is over a period of 50 years, that's when our x value is 50. So I press 50 on our keypad and our spider jumps to that value. So that shows us for the blue graph, our coordinate is 50, 19.2. I label the points there. So that means for our blue graph, let's remind ourselves of which blue graph that was. That was for the one that started a bit lower. So let's draw a curve to show exponential growth. Next, for our red graph, I jump to the next graph and I press 50. And that shows us that the coordinate is 50, 6.8. So 6.8 around here. And we make that curve grow exponentially as well. Then at the end, there's one more point of interest, which is the intersection. So let's exit the trace tool by pressing escape and enter the analyze tool menu, 6 for analyze graph, then 4 for intersection. We take this dotted line, we give it a click on the left side of the intersection, then drag it to the right side of the intersection. And what we get is the following coordinate. Rounded to 2 decimal places, 12.56 and 2.41. And we've sketched our graph. Make sure that your graph does not go past these endpoints, because that is how the domain has been stated. Let's answer the following questions. Find when the population of state P is equal to the population of state Q. So that implies that these populations are equal. In other words, what we can do is take these rules, which are given to us, and make them equal to each other. Now there's a couple of ways we can solve for it. You must make sure you write down this line, because that shows what you're making equal. The two ways to solve it are, well, firstly, you've already got the value of time from your coordinates of the intersection, because where they intersect, that is when they meet each other vertically implying that the populations are the same at this point in time. So the population is 2.41 million, but the time that it occurs is 12.56 years after 1950. So T is 12.56. Lastly, to answer this find when question, you need to answer it very precisely. Well, in terms of the information that's given in the question. So T would be years after 1950, which means you can answer this as mid-1962, because 1962 is 12 years after 1950. The other way you could have solved this is in your calculator. In your calculator's calculator page, just to use the solve function. Now let's answer part B. Part B, find when the population of state P is twice the population of state Q. In other words, P would be twice of Q. In this case, I take the rules, which are given to us, and substitute them into this equation. We get 1.2 times 2 to the 0.08 t equals to 2 times 1.7 times 2 to the 0.04 t. Now for this particular question, it's going to be a lot harder to find the time when one population is twice the other. In fact, what it's asking us to do is find, for example, when the height of this graph is twice the height of the other graph. Not as easy to do in our CAS. But what we can do is solve it using the solve function. So let's do that now. Menu 3.1, solve. 1.2 times 2 to the power of 0.08 times t. And that's equal to 1.7 times 2 to the power of 0.04 times t. Okay, and let it solve for t. Oops, I've made a mistake. I've forgotten to multiply the other one by 2. So what I'll do is I'll copy and paste that previous line. To do that, you press the up arrow until it's shaded, press enter, and it brings it down. Very quick method of copying and pasting. So place arrows around the second rule and multiply it by 2. Okay, and our answer for time would be 37.56. To answer this as a question to the number of years after 1950, we should get around the middle of 1987. Okay. Now at this point, we're done with this worksheet. But I also think it's important for you to know how to fit data using your CAS. Now I'm going to prepare this worksheet. Give me a moment to rough some things out. And what we're going to do is use our CAS to fit some data. Okay, hopefully you can see all this. Now, what happens when we use exponential models in science is mostly when we do experiments and we take data and we see whether our data fits some theoretical model. So in this example, our data is based on the increase in weight of Somu, an orangutan born at the Eastern Plains Zoo. I'm taking this example from page 466, example 25. So the data is given to us for the first 6 months of Somu's birth, and what they want us to do is fit this to an exponential model. Okay, so let's use our calculators to do this. Now to enter data into a table, the particular application we use is the lists and spreadsheets page. So I'm going to do that by pressing Control Doc, and I go to option 4. Add lists and spreadsheets. And then we get a table that looks like our table of values. But instead of going sideways like our table of values, it goes downwards. So I'm going to follow these steps. We've done step 1. Step 2 is labeling our columns with the pronumerals that's given. So the pronumerals given for month would be M and weight would be W. The way you enter the M and W would be in the top entry for those respective columns. So I navigate up right to the top, and I call column A M for weight, press enter. Then what's going to happen is any value that's entered in this white part will be attached to the pronumeral M. The second column we'll call W for weight. Now for M, what I'm going to do is enter the values from 0 to 6. 0, 1, 2, 3, 4, 5, 6. Before I enter the values for column W, I just want to point out the extra horizontal line there that has an equal sign at the front. Now what our table does is it can also help us populate a table of values based on a rule. So a rule, for example, could be W equals 2 times M, just as an example. Now to do that, so we're doing a bit of an aside from the question we're doing. So this is just a bonus part. To make all of the numbers here doubled by following the rule, we can make W equal to 2 times M. See that M there is bolded? That's because the calculator has saved some values to the pronumeral M. So press enter and the calculator is going to ask us what M means. Does M mean the column, or does M mean the individual values as part of pronumeral M? And what we're going to do is call it the variable. We're going to consider M as individual variables. Okay, we press enter, and what this column has just done is it's populated the table of values. Now you can make the rule as complicated as you want. Let's call it 2 to the power of M. And it does the same thing. Now back to our question. Our question was to enter these values into W. So let's get rid of that rule and let's enter these in. Okay, so at this point our calculator has the exact same table of values that we have. What we're going to do, so by the way, we've finished part 2 and part 3 of our steps. We're going to go to part 4, and that's what the calculator is going to do, is take these as coordinates and plot them in a graph. So open a data and statistics page. Control Doc. Data and statistics will be part 5. And then each of these blue dots represents a coordinate. So it's up to us to tell the calculator which pronumeral is the horizontal axis and which pronumeral is the vertical axis. To change them, we can press Tab. So we're up to question 5. Tab. Tab to cycle between your two axes. And we know our horizontal axis should be our independent variable. So independent variable would be the months M. Then cycle to our vertical axis, which would be W. And then what you should see is what seems to be like a set of dots that are going upwards. Now it's not going to be the exact same as an exponential growth graph, but what we're doing is we're trying to fit this to a model. Now this is part 6, fit model, and we're going to tell our calculator to fit it to an exponential model. So we do that through menu, then 4 for analyze, then 6 for regression, and at this point there's a whole bunch of different models we can fit it to. Now we're trying to fit it to an exponential model, so let's go to option 8, and our calculator has plotted kind of like a line of best fit through all these points. I'm going to write down the equation that you see on your CAS, and let's interpret it. To 2 decimal places, what you should see is 1.55 times 1.22 to the power of x. Now in terms of our pronumerals W and M, we should change it, the x and y's into those. So we get W is equal to 1.55 times 1.22 to the power of x. Now notice what you see here. We have a coefficient of that power. That coefficient, remember, represents our initial amount. Oops, I think I've just made a mistake. That x there should be an m. Okay, so initial amount, that's when our value of m is equal to 0. That's our initial time. Okay, that other number there is our base of the power, 1.22. Now this number is greater than 1, which indicates growth. The particular growth we expect to see is 22% growth per month. 22% because every time we multiply by 1.22, our number increases by that 0.22. Now in terms of this question, that tells us that Somu, on average, has been growing at 22% in terms of their weight per month. And that's how an exponential model can help us find these other particular things. One more thing I'll add, this will be the last thing. The initial amount, notice that it wasn't the exact same as the actual initial weight. And that was because the calculator tried to fit that curve, and that curve turned out to be slightly less than your initial value. And that's okay, because this is just a model of what's actually happening. Now, I think that's it. I hope this has been helpful, and good luck.